you've got protons hopping from the K path and through the D path, and you've got electrons coming down all the time. So they're all meeting at the second binuclear site. Does that make sense? Right here, we don't know the complete story, but right here at the end of the K path is a tyrosine. Tyrosine 244. So keep that in mind as we discuss the next thing. Again, I wish we knew all the answers. We don't. So I'm going to fill you in the best we can. So the second binuclear site is the cytochrome A3 that has heme A3 in it. It's a protein in subunit 1 here that has this heme in it. And this copper right here is CuB. And they're so close together, they act as one. All right. In years past, we would just write this out. I thought I would cut you a break and have some of this already on the screen for you. That doesn't make it easy. This copper here begins in the +2 state. This is CuB. It's coordinated, that is bound by 3 histidines. These are part of the protein. The weird part is that histidine 240 is covalently attached to that tyrosine I just mentioned to you, which is at the end of the K path, and that's tyrosine 244. So we've drawn this portion right here. This portion here, we're blowing up. That's this down here. Here is histidine 240. Here it's its side chain imidazole group. But there's no double bond here because you're making a bond from one nitrogen in the histidine, that would be up here, to the copper. And you're making another bond to the aromatic ring of tyrosine. This is very strange. You don't see this normally. And yet that's part of how this thing works. So what's happening here is that this metal, with its +2 charge, is sucking electrons through this pi cloud here. These nitrogens have pairs of electrons on them, away from this hydroxyl group. So in other words, there's this path like this, where the electron density on that OH group is being weakened, pulled away. The last time we talked about this kind of thing was in conatase, where the iron of that cube was pulling electrons away from that hydroxyl group. Here it's a copper ion, a metal, that's pulling electrons away from this oxygen, allowing this proton to want to come off, which results in a lower pKa. So apparently this connection is so that this tyrosine can participate in donating a proton. So it's one of the guys that's donating a proton to oxygen, the oxygen that's going to bind, that gets reduced to water. It's not the only proton. This is just one thing that's contributing to this. So we have a partial understanding. Here is the heme with the iron. The iron starts off in the +3 form, just as the copper is in the +2 form. And so that's why I've written this as, this is the fully oxidized binuclear complex. Both metals are in the highest state to begin with that they can be without something weird happening. And then it turns out that there is a hydroxyl group, an OH minus. This iron has 6 binding positions. The corners of this rectangle are the nitrogens that are in the heme, holding it. Down below is a histidine, H, a histidine, on the protein. But above it is sitting this OH minus. And so I'm keeping the oxygen atoms in red in this diagram as we go through this. Okay? So here we go. Over here, this is just a shorthand notation of all of this, because we don't want to write all of this all the time. So in comes an electron. Where's the electron coming from? Where does it originate? Cytochrome C. The cytochrome C dot. In comes an electron. And what's happened? The iron is still in the +3 state. It still has this OH minus on it. But notice the copper is reduced to a +1. So the electron goes to the copper first. Then a proton comes in. We don't know which proton is this first proton. Is it from the D path or is it from the K path? We don't know that for sure. In comes another electron, and off comes a water molecule. And so that water is this OH minus, which I guess I could have put here. I just was trying to keep this simple. It's this OH minus reacting with this proton to form water. So the first water actually comes not from O2, because O2 hasn't even entered the picture yet. Remember, oxygen is O, double bond O. It starts from a hydroxyl group. Now, with that other electron, the iron is in the +2 state. So the copper is reduced, the iron is reduced. This is now the fully reduced complex. It can't get more reduced than this. In comes the oxygen finally. Remember, this is the oxygen that is diffusing randomly. It can cross membranes because it's nonpolar. That oxygen is now going to bind to the iron because just like in myoglobin and hemoglobin in BIS 102, oxygen can only bind to iron in a +2 state. So here in comes the oxygen, and this iron, which is part of this heme, we've just left out the heme part to keep it simple, can now bind that oxygen at an angle. And it's actually so close, it's forming a bond to the copper itself. A small, minimal bond. The main bond is to the iron. So this is a weak bond between the iron and the oxygen. Are you okay with that? Now the oxygen comes in. And now this is where metals can come to the rescue. There's an electron rearrangement. Metals can expand their valence. That's one thing cool about metals. And so these guys can't donate, the metals can't grab any more electrons, but this iron can donate electrons. And the oxygen is very electron withdrawing, saying, give me those electrons. So we get this. Wish you hadn't shown me that, Dr. Hill. The iron has gone from a +2 state to a +4. It says here, I'll give you 2 electrons. And in rearranging the oxygen, which is over here, this one is so close as to be nearly touching this copper. The copper is going to grab this thing and become an OH minus. And this H, along with 1 electron, has actually come from the side chain of the tyrosine. So the tyrosine, as I said earlier, donates a proton. It's also donating an electron. So it's part of the circuit. This whole thing is part of the circuit. So this tyrosine is able to, because it's so close, it's right in the mix, it was right in here, This OH is so close to what's happening here. It can donate a proton and an electron and still be stable because this is now a free radical. But remember, the side chain here is an aromatic ring with this oxygen. That free radical is spread out over that aromatic ring. So it's a safe thing to do. We'll see this later. So make a little asterisk here. We'll see a different tyrosine participating in something similar when we talk about photosynthesis. So tyrosines are often called upon when you need the transfer of one electron. Same here. So now you've split the oxygen atom molecule. One oxygen's over here, one's over here. Now an electron can come in. Where's that electron coming from originally? Cytochrome C. So every time an electron comes in, so right now we've had two. One up here, one down here. Every time an electron comes, pardon me, one up here too. Every time an electron comes in, it's a cytochrome C that's docking. Without that, there's no electron. Two protons are now added. Where are they coming from? The proton channels D and K. Which ones, we don't know for sure. Those are those two channels, one red, one green. They're hopping through. Now a water comes off. So this is your second water. Remember how oxygen, an O2 molecule, generates two waters? Here's one down here. Here's one up here. It's just not occurring in the way the humans might have thought it might occur. Now we've got this iron still with its oxygen bound to it. This thing will get one last electron. Remember, there's 4 electrons that are donated by those 4 cytochrome Cs coming one at a time. And now this is going to give us, with the proton coming from the channels, the OH minus group. And now we're back to square one. This thing here is identical to this thing up here. So what I would like you to know for the final exam on this part is take a step or two away and get the bigger picture. Understand who's doing what. I would never ask you to draw this all out. But I'm trying to get you to see how this fundamental reaction on this planet appears to occur. Cool? Because this is what's happening in all the mitochondria, and the mitochondria apparently originated from bacteria. In bacteria, this is occurring in their inner membrane. So everybody on this planet pretty much is using this scheme. Are there exceptions? Yes. When organisms are anaerobes and they don't use oxygen, but most are aerobic. So the last thing is to take a little bit closer look here